Hello and welcome to this video on magnetism and electromagnetism. Like gravitation, magnetism is a field force, which means that objects don't actually need to be touching one another to exert a force on each other. Magnets are materials that have a magnetic field around them. This is a region in which a magnetic material will experience a force. Most materials are non-magnetic and will not experience a force. A lot of students, maybe at Key Stage 2 in primary school, will have had a look and used the bar magnet to sort out magnetic from non-magnetic materials. But it's probably well worth a revisit in secondary school. Particularly include some metals that are non-magnetic, because many students will have the misconception that any conductor of electricity or any metal is magnetic, but only some of them are. The iron, steel, nickel and cobalt are the only magnetic materials. A nice thing to show is this floating paperclip here. The paperclip must have balanced forces on it because it's stationary. It's going to have the gravitational force of the earth pulling down on it, also the tension in this thread. So it must have an upward force to balance it, and that is exerted from this magnet, holding it up, pulling it upwards. As a teacher, it's useful to have an insight as to why some materials are magnetic and others are not. Magnetism is to do with the behaviour of the electrons in the material. We can think of electrons as tiny magnets. Regions of a material in which the magnetism works the same way are called domains. This model here shows them. So in non-magnetic materials, all the domains are arranged randomly and are going to stay that way. So in objects such as this iron nail here, the domains are all random. It's not magnetised and there's no force of attraction between the nail and this paperclip. But we can force those domains to all line up, either by stroking with a magnet or passing through a current carrying coil. Once our domains are lined up, it will become magnetic. So let's have a go. And now our nail is attracting our paperclip. All magnets have two poles, a north pole and a south pole. The magnetic field is strongest at the poles. When you have two like poles coming together, they repel one another, as you can see here. Unlike poles will attract. If you have two materials where the force is always attractive, regardless of the orientation, then one material is a magnet, but the other is just a magnetic material. There are lots of ways to visualise magnetic fields. The classic way is with a bar magnet, a piece of paper and some iron filings in a pepper pot. I'm going to put some safety goggles on because the iron filings can be very dangerous if they get into your eyes. So if I put my piece of paper over my magnet, I've just suspended it so it's nice and flat, and then shake my iron filings onto the paper, you can immediately see those iron filings being attracted to the poles, showing quite clearly that those are the most strong points of the magnet. So now we can see the shape of the field lines, sort of radiating out from one pole and coming back round into the other pole. A safer way to use iron filings is to contain them in a container. Here, rather than iron filings themselves, I've got finely snipped steel wool suspended in cooking oil, and that is actually really nice for showing a magnetic field. So hopefully you can see as it starts to settle sort of the curved field lines at the side of the magnet there. And we can also see two repelling magnets, where we should have an area in the middle that's pretty much empty of our iron filings, showing the neutral spot between the two magnetic fields.
Okay, now Ellen has shown you some great ways to make magnetic fields visible and experiments that the children can do in order to be able to explore magnets further. Now, following on from that, they may well draw down the diagram of the magnetic field around a bar magnet, and I find that they generally remember that pattern quite well. But the question is, how well do they understand what those field lines are actually showing them? Here's another little demonstration that you can do, which will help to make that a lot clearer. I've got a bar magnet here perched on the side of this trough, which is full to the top with water. And what I would really like is to be able to have a north pole on its own. Well, you can't have a magnetic monopole. Magnets will only come as magnetic dipoles with two poles. But what I can do is I can put a bar magnet through the middle of this cork with the south pole quite a long way below, so that its influence will be a lot less. And then I can treat this a bit like a floating north pole all on its own. I'm going to put this in the water about here, and I would ask pupils what do they think is going to happen. Having learned everything that Eleanor covered previously, some might say it's repelled from the north, others might say it's attracted to the south. Let's watch, see what happens. Of course, what is happening, it's doing a little bit of both. Repelled from the north at first and being pulled round and attracted into the south. I usually find that before the magnet gets into the south, somebody in the class has said, that's what those lines mean, isn't it? So now we can have a nice definition of what the field lines mean, because the field lines tell us the direction of that magnetic force on a floating north pole. And understanding that will help them much further on in their education when they come to look at magnetic fields of different shapes and sizes.
Magnetic fields can also be seen using a plotting compass like this one. It is in fact a tiny magnet suspended about a central pivot point. We can think of it very much like this magna probe I've got here, which you can clearly see is a little baby magnet suspended so it can pivot in all three dimensions. With this, we can clearly see the repulsion of the red north end from the red north end of our magnet, and we can see the attraction of the north end to the south pole of our magnet. And what's lovely about this is we can see the 3D nature of the magnetic field. Well worth getting. They're quite cheap, only a few pounds. Comparing this to our plotting compass, we can see we've got a similar thing happening. We've got our needle pointing away from the north pole of the magnet, which means our compass needle, the point of it, must be a north pole being repelled by the magnet, by this magnet here. And we can move our compass around our magnet until it points again at the south pole. You can get your students to start by positioning the compass in various points and tracing the path of the compass back round to the magnet to show a build up and show a field pattern of the magnet. We have an interesting issue though. When we actually consider what happens with the Earth's magnetic field, we know the Earth has got a magnetic field. You may be used to using compasses like this to help find your way around. But what happens is our compass needle is always going to point to the geographic north of the world. I can show it again with my little magna probe here, that it's the North Pole that's being attracted to the North Pole of the Earth. And the South Pole is attracted to the South Pole of the Earth. What this means, therefore, is actually at geographical north, rather than being a magnetic North Pole, it is in fact the South Pole of a magnet. This can cause a bit of confusion for lots of children, so do beware. To add to the confusion, the geographic north and the magnetic north are not in exactly the same place, and the magnetic north does move around a bit, and even occasionally, about every 10,000 years or so, totally flips entirely, so we end up with the reversal of the Earth's magnetic poles. As mentioned before, magnetism is due to electrons aligning. It's maybe not very surprising, therefore, that when we've got a flow of electrons in an electric current, that they themselves have their own magnetic field. David is now going to do a demonstration to show this effect.
Okay, so as Eleanor has just suggested, if we have an electric current flowing in a wire, there will be a magnetic field associated with those moving electrons. Here's a very simple demonstration that can illustrate that. So what I want is a long straight wire, which I've got heading down through the board here, and it's connected simply to my power supply. Now when I turn the power supply on, I'm effectively putting a short circuit on the power supply because I've got no resistance apart from what is in this thick copper wire. So it's important that you use a power supply that can actually handle that situation. Okay, so we would like to investigate what the shape of the magnetic field is around this wire. And, as we've seen previously, you can do that with plotting compasses. If I arrange these plotting compasses around the wire, they are all more or less pointing in the same direction at the moment. But watch what happens to those plotting compasses when I turn the current on. Clearly they detected a magnetic field because we saw them move, and if you look closely you can see that they've all lined up tip to tail, all going round in a circle. My overlay here shows what the result of using many plotting compasses would tell you about the shape of the field. That the field lines this time are concentric circles centred on the wire going round and round. They're closer together nearer the wire because that's where the field is stronger, further apart at the outside where the field is weaker. And I've got arrows which show the direction of the field, clockwise when viewed from above. What does that mean? Well, if you think back to the floating magnet experiment, we know exactly what that means. It means if you could set this up in a tank of water and put your floating magnet in, then it would spend all day going round and round in a circle, following the arrows, going clockwise for as long as the current is turned on. Okay, you might be wondering exactly how we would know, how we would work out that the field lines in this case are going clockwise. Well, electromagnetism is full of little ways of working things like this out, and in this case we use what we call the right hand grip rule. You need to grip the wire in your right hand with your fingers curled round, and you put your thumb in the direction of the current. Well, in my power supply the current is going from the positive up this side, and then it goes down through the middle of the board there and back round to the negative. So with my right hand I'm going to grip the wire with my right hand, curl the fingers round with my thumb going down through the board, and my fingers are now curled round in the direction in which the field would be going. That suggests that if I reverse the current, the field will also change direction. Let's see if we can pick that up with the plotting compasses. So I'll start off by putting them back around the wire, and then like before we'll turn on, see which way they are turning, and then if we can reverse the power supply, let's see if the plotting compasses will also change direction. There we go. Okay, so what we've got here is an interesting scientific curiosity, but what we'd really like to do is to be able to take this and turn it into really practical, useful devices. So we need to find a way of making this fairly weak magnetic field much stronger. Here's a start. I'm going to disconnect my single wire, put that to one side, and bring this one in. Now this time I've got one piece of wire, but I've coiled it round and round. The idea being that every loop of wire will contribute part of a much bigger magnetic field. We can put the plotting compasses on again to help us understand what shape that magnetic field will be. We'll put those all around like that, and let's see if we get a reaction from them when we turn the field on. Okay, quite a reaction from the compass needles there. Just remove those and then you can see the shape of the field on my card overlay here. In fact, what you end up with is a magnetic field which is shaped very much like that of a bar magnet, except now it's an electromagnet. We can perhaps understand why the field is that shape if we think about the previous example with the single wire and our right hand grip rule. In this case, current is coming in from the positive, around here and around the loops of coil like that. If we think about the wires down this side and use our right hand grip rule for wires which are going down that way, then my fingers would be suggesting that on the outside of the coil the field is coming this way. If we apply it on this side, where the current is coming up, then on the outside my fingers are telling me that the field will be coming this way. And similarly, it will turn at the ends and go through the middle of the coil. So maybe now we're heading towards something which will give us a more practical and stronger electromagnet. I'll now let Eleanor pick up the rest of the story.
So David has just shown us how a current carrying wire has a magnetic field and how we can increase the strength of that field by looping the wire into a coil. That's similar to what I've got here. I've got some more turns than David of wire coiled around a pencil. When I turn on the power, we're going to see if we've got enough strength in our magnetic field to pick up a paperclip. Let's have a look. Not a lot going on there. But let's see what happens if I replace my pencil with an iron nail. Turn on again. And now we are picking up the paperclip. And when I turn off, the paperclip drops. We talked earlier about classifying materials into magnetic materials and non-magnetic materials. But we can further classify our magnetic materials into soft magnetic materials and hard ones. Substances like our iron magnetise easily but lose their magnetism quickly. So when I pick up this, turn on the power, I can pick up the paperclip, but as soon as I release the power, the paperclip drops because it loses its magnetism. Substances like steel have a different structure, and once magnetised, they will keep their magnetism and become permanent magnets. We call these hard magnetic materials. So we've seen one way to increase the magnetism of our electromagnet is to add an iron core, a soft iron core. But even with that, my field is only strong enough to pick up one paperclip. I have another coil here with far more turns on it. Let's see what happens when we connect that to the power supply. So now, an identical nail, same power supply as before, same power. I turn on. So, adding an iron core, increasing the number of turns, and also increasing the current from the power supply will also increase the strength of the magnetic field of our electromagnet. So now, with an electromagnet, we have a magnetic field that we can turn on at the flick of a switch, but crucially turn off as well. These have got loads of practical applications. They can be used, for example, in recycling centres when we want to sort our steel cans, which are magnetic, from our aluminium cans, which are not. They can also be used in buildings and fire doors. Fire doors are held open by an electromagnet, but then in the event of a fire, the magnet releases and the doors will automatically shut. There are many more applications of electromagnets, and you can see more about these in our other video on the motor effect, when we'll be looking at loudspeakers, motors themselves, and many more applications.